having us here today. Without further ado, I'll get into the agenda. So I'm going to have a brief introduction to us as a company, what we do and how we do it. And we're going to give you an example there of how we engaged on a specific project so that you can see how we tend to engage with the supply chain. And then, as Simon said, I'm going to talk about ground source applications. So the main of the session will actually be not in PowerPoint as we are at the moment, but in a whiteboard. Please do ask questions because it really does help me to keep the thing on track, keep the presentation on track and answer the questions that you're interested in if you do engage with this. What Duncan will do is he knows what's coming, as it were, in the presentation, so he will ask the questions at the most appropriate time. So don't worry if your question seems to have been ignored, Duncan will be coming back to it. As Simon said, we're going to do some myth busting as well, talk about solar and ground source, talk briefly about deeper ground source and ground source as a long-term asset, which is a very exciting part of the industry at the moment. We will have time at the end for more questions, but as I say, please do ask them as we go through so I can keep it most relevant to yourselves. So who are we and what we do is, as Simon said, we've got well over 20 years of experience in ground source. Part of that was in the contracting side of the business. So, you know, I've stood in the plant room wondering why the thing isn't working, but now we are a design house and we'll talk about what we do in a second. There's well over 650 megawatts of systems installed over those 20 years that we've been involved in designing. And what we're all about is providing that specialist input to give your project substance, which in turn then lowers risk for yourself. It does unfortunately often happen that the advice that's given by non-specialists in this area, you know, is incorrect. So I think it's important to get the specialist advice, and it's all about giving your customers the best possible information. We've worked with a huge number of companies, lots of end user like universities, for example, but also other mainstream large consulting engineers and contractors and so on. So a broad range of customers for in our portfolio. So what I'm going to do now is just give you an example of a justice centre in London, where we engaged with a large consultant to establish, first of all, is ground source feasible? So it was an informal early engagement. We don't tend to charge for that type of advice. It's just answer a couple of emails, maybe do a call, something like that, just to understand, you know, are we crazy even thinking about ground source at that stage? Then we followed REBA stages in this instance. So at REBA stage 2, we did a feasibility study, which included a desktop geological investigation. So no need at that point to go to site and do actual on-site investigation. We actually did a preliminary ground loop design at that point. And that's quite important that we do that, because rule of thumb design, even at early stages, can be very, very misleading indeed. So that preliminary ground loop design, we actually use the same process, even early days, that we use right down the line when we're doing a detailed design on a system. And very important at REBA stage 2 is understanding what that system efficiency looks like for the energy statements and so on. Then on to stage 3, much more design assistance. So workshops with the client, for example, on this project particularly, there's quite an odd basement structure in there. So with pipes coming up into the basement from beneath, we did quite a lot of work on the structural input and the structural impact of that. More cost analysis, project program, and so on. And then finally, at the end of REBA stage 3, we specified a set of specialist packages for test bores actually physically on the site, which were carried out between stage 3 and 4. We then went on to stage 4, which was detailed design. So that's a full system specification. By the time we get to this point, though, we're doing a lot more support. So it's a lot more meetings rather than formal reports and so on like that. And then finally, what we're actually up to at the moment is ourselves and AECOM, who are the consulting engineer involved in it, we're novated over to the main contractor, and we are effectively working in a role to support that process going forward. So I'm going to drop out of this and into my whiteboard now. And what I'm going to do is, if it starts up for me, is give you a quick introduction to the technology, how it works, give you a very brief overview of how the design process works, and then I'm going to talk you through some system types and the considerations that are associated with those different system types. So I'm very conscious of the fact I'm with an engineering community at the moment, so I won't go into how heat pumps work in too much detail, but I'll just give you a quick overview. So heat pumps are just a box that moves heat from a cold place to a hot place. And that's a simple explanation of really what it does. It just takes heat from a cold place and puts it in a hot place. That, of course, doesn't tell you how it actually does that. And how it actually does that, it manipulates the pressure in a gas liquid circuit to allow that gas to evaporate at a low pressure and low temperature. It then goes through the compressor, which increases the pressure. It then condenses at a high pressure, high temperature. So we're effectively picking up heat on this side and delivering that heat back in the other side. There are a couple of other points to make on the process. First of all, it consumes electrical energy. So the compressor itself consumes electrical energy to make it run. And there's another little piece here, which is the thermal expansion valve at the bottom. And that's just a pinhole, which keeps the high pressure on one side and allows the low pressure to develop on the other side. So a very, very simple high-level overview. All the heat pump does is it manipulates the pressure in that gas liquid circuit to pick up heat at a low temperature and deliver it in at a high temperature. Any questions on the chart so far, Duncan?
No, you're fine for a glass of water, Chris.
You can tell, could you? Right, so let's now have a look in a little bit more detail at ground source specifically, and just touch on the design process that we go through for these systems. Little bit of terminology first. The heat we are taking from the ground in heating mode, this is heating mode and this is cooling mode over here. And I'll go into heating and cooling systems in a little bit of depth in a second. The heat we are taking from the ground is called the heat of extraction, the heat being extracted from the ground. And we put heat into the building, and that's termed as the heat of rejection. There's another bit of energy involved, which is the electrical energy being consumed by the heat pump. And almost all, in fact, to a very, very close proximity, almost all of that electrical energy through the forces of friction ends up as heat as well. So the heat being taken from the ground is effectively added to by that electrical energy. So our heat being rejected into the building is very, very close to equal exactly the heat being extracted from the ground plus the electrical energy being consumed. In cooling mode, it's the same but in reverse. So the heat being extracted now is being extracted from the building, and the heat being rejected, is into the, how do I get rid of that then? Just minimize it down there. The heat being rejected is now being rejected into the ground. And again, our electrical energy is being consumed. And again, almost all of that is ending up as heat. But in this case, it's now being added to the heat being taken from the building and it's put into the ground. So in a very real way, the heat, the electrical energy, that's being consumed by the heat pump actually helps us. It adds to the energy coming from the ground in heating mode, but it hinders us in cooling mode. So the processes aren't exactly identical. The other point I would just make at this juncture is that the efficiency of the heat pump depends on the difference in temperature between the source and the load. So the bigger the lift that's being undertaken by the heat pump, the more electrical energy it's going to be consuming and the less efficient the process is going to be. And I'll come back to that in a little bit more detail in a few seconds. So the design process then centers around, we tell the design software what heat is required being rejected into the building and what heat is being extracted from the building. We also tell the design software what the properties of the heat pump are, because the ratio of the heat of extraction, heat of rejection, and electrical energy does depend on the product itself, depends on the type of heat pump that's being deployed, depends on the refrigerant, the architecture of the heat exchangers, and the compressors, and so on. So we have to tell it what's going on in the building, what the properties of the heat pump are then. And the question we ask the design software is, how much pipe do I need to put in the ground to ensure that the temperature in the long term is sustainable in this ground loop? And if I draw a little graph of that to illustrate it, let's do a heating only system first. Every year the loop will get slightly colder, but what we don't want it to do is just continue to get colder and colder and colder until the heat pump can't suck heat out of it anymore. What we want it to do is tend to a limit and flatten out in the long term. And if we look at a heating and cooling system similarly, then it's the process goes from winter to summer. like so. And what we don't want it to do, again, is just continue to get hotter or colder. We want it to tend to a limit. So that is a very high level summary of the design process for ground source heat pumps. It's all about how much pipe do I need to put in the ground, given the properties of the heat pump and given the requirements of the building, how much pipe do I need to put in the ground to make sure that we've got a sustainable system in the long term. And that's in a nutshell how the design process works. Any questions so far, Duncan?
No questions in the chat.
Okay, cool. So if I now move on to what these systems look like then in the real world, this would be a very typical heating and cooling ground source system for a commercial building. So what I've got here is one heat pump cooling. So that heat pump is putting heat into the ground loop, and I've got a couple of heat pumps here heating, so they're taking heat back out of that ground loop again. So right away you can see that energy recovery is going on in this header. The energy that's being taken from the building in the cooling circuits is being put back into the building in the heating circuits. But it doesn't just stop at instantaneous heat recovery. It actually extends to interseasonal energy recovery, because this ground loop can actually store energy in the long term. So it's the only technology really that at scale can store energy between summer and winter for heating and cooling buildings. And that's one of the key advantages of ground source. I'll come back to it later, but these systems which have got heating and cooling going on are by far the most efficient types of heating and cooling systems, particularly in commercial buildings. Just to talk about how this then interfaces with the building, what I've got here is I've got what's called a sliding header, and in this mode we've got one heat pump cooling. These two valves here will be shut, and these two valves will be open. And as the cooling load increases, what we would then do is we would shut these valves and open up these valves and reverse this heat pump onto cooling mode. So we can flexibly match the loads in the building with this type of architecture. Now, there are other architectures for heat pump deployment in buildings. There's at least 6 different architectures which are common out there, but this is just an example of one that's very commonly used in the UK. Few things to consider on this. I mentioned the importance of building loads earlier on, and as a minimum, we really require a monthly breakdown of those heating and cooling loads in order to design a ground loop adequately. But also, when we're looking at a more complex system like this, we do need to understand what those loads look like throughout the year, and ideally an hourly load profile would give us the best resolution on this. And an example of something that can happen with these systems, that a mistake that could be made is, let's say, for example, we've got a small, say 10 kilowatt server room load that's running all year round. And let's say this heat pump is 100 kilowatts of capacity. What we don't want to be doing in the middle of winter is reversing a 100 kilowatt heat pump, turning it on to deliver a 10 kilowatt load, because that's going to be inefficient. It's going to mean the heat pump's going to be cycling on and off. It could be bad for product longevity. So if we do understand we've got these types of loads that are in mixed seasons, then one thing we could often do is just dedicate a little heat pump to that cooling load connected up to the ground loop. So you do need to understand the loads in a little bit more detail than perhaps you'd be used to with conventional technology, not just to design the ground loop, but to then select the heat pumps as well. Anything on the chat, Duncan?
Yeah, we've got a couple of questions based around how the ground temperature changes. So do we include analysis of possible freezing effects of the ground and results on the long-term heat pump output when selecting?
Yes, we do. Yeah, absolutely. So we'll be modelling the ground loop temperatures in the long term. The industry minimum is a 20-year model. Very often we're modelling up to 100 years and beyond what that temperature in the ground loop is going to do. And we'll be considering the effects of that on the ground and also on the efficiency of the system overall. Yeah, absolutely.
Yeah. And a frozen ground only implies it's a poorly designed system. The ground should not be freezing.
Yeah, absolutely. We do use negative temperatures in the ground loop. That's perfectly normal. Normally we're going down to about -4 going out to the ground and about 0 coming back. But that's well within the capability of the heat pumps, first of all, and also isn't going to cause any adverse effects in the ground. On the hot side, incidentally, when we're cooling and that ground loop starts to get warm, we could be up to 35, 40 degrees going into the ground.
How do we mitigate the process of cooling the ground, and what to take into account during design?
Okay, so what's going on in this ground loop is we are establishing a temperature difference between the water in the pipe here on the ground out here at say 12 degrees C. And as we establish that temperature difference, heat then flows in or out to equalize that temperature difference. Heat flows from the hot to the cold is the physics description of it. So what we are doing is we are putting enough pipe in the ground, a big enough heat exchanger, if you like, in the ground, that the process of net flow of heat out of the loop or net flow of heat into the loop is balanced by what we are taking in and out of it. So we're establishing a temperature difference which naturally equalizes, and that's how the ground loop physically functions.
There is one more question. It's up to you whether we move on to it at a later stage. How deep is the average loop? And geographically and geologically, I'll add, what are we looking for?
Okay, I'll come back to the depths of ground loops in just a bit. In terms of geologically what we're looking for and geographically what we're looking for, we do a detailed geological analysis of the location that's involved. That naturally has to be specific to that location because the geology does change. We're looking at things like what different layers of ground do we have. So in a ground loop like this, we might be going through several different layers of ground condition. There might be an aquifer down there, for example. There might be water flowing in that aquifer. So we need to understand all of those conditions, and they are very much site specific. But I'll come back to depths in just a little bit. Brings me on to the point. I'm talking primarily at the moment about closed loop boreholes in systems, but I will come back towards in a little while to look at other types of systems as well. Okay, anything else on the chart, Duncan?
No.
Okay, so let me talk about some system architectures for you here. So this is an example of a district heat network that's got central ground source heat pumps in it, and that's then delivering up a high temperature riser to heat interface units in the dwellings. I've drawn it as a tower block, but it could just as well be a low-rise development with individual houses, for example. And each of those heat interface units will be delivering domestic hot water at maybe, let's say, HW at say, let's 65 degrees C, let's say, for example, and it will also be delivering space heating. Now that space heating could be as low as maybe 35 degrees C, but because we've only got one riser, because we've only got one heat interface unit, we'll have to run the whole system at the highest common denominator, if you like. So we have to run the whole lot at that domestic hot water temperature. So back to the point I was making earlier, the efficiency of these systems is dependent on the temperature difference between the source and the load. We are compromising that space heating efficiency. We could be doing that at a lower temperature because we've got to deliver that domestic hot water. So there's a compromise with this central plant solution. The other thing to point out, however, is that there is a sale of heat in here. So the kilowatt hours of heat can be sold into that dwelling. So commercially, there is a sale of heat involved in this. Now, there is an alternative to that, which is to distribute heat pumps around the building. So right away, you'll notice that we've got no central plant now. We've got no central pumping. All of the pumping in these systems is done by the tiny little pump inside the heat pump. And in each dwelling, we've got a heat pump, which can be delivering our domestic hot water, again, at, say, 65 degrees C. But now what it can do is when it's finished doing domestic hot water, it can turn off, reduce in temperature, and now run the space heating at 35 or whatever that's selected at. So there isn't that efficiency detriment that you get with a centralized plant solution because you're having to run everything at the higher temperature. Notice, however, that all of the run costs in this apartment here are associated with the electrical energy consumed by that heat pump. Electricity is a regulated commodity, and so the homeowner has every right to buy that electricity from anybody that they wish. So there is a different set of commercials, and while the efficiency of the system with the more conventional district heat network is compromised, there are the sale of heat agreements. So what we do quite a lot of is studies looking at the two alternatives. And whilst this one technically tends to come out the better one, it doesn't always go in because of that sale of heat agreement, which could enable the construction of the heat network in the first place. Just incidentally, in terms of installed costs, these two solutions are almost identical in terms of install costs. I think we priced up a system that was about a £4 million system for a large district heat network about a year or two ago, and there was only about £4,000 difference when you looked at the overall solution between the two. So it doesn't necessarily mean that one is more expensive than the other.
Yeah, the main reason for that is all the very expensive, highly insulated pipe you need on the centralised plant.
Absolutely. Okay, so that's the different district heat network approaches on the system. I'm just going to talk very briefly now about system hydraulics and how we build these systems up. And these could be distributed heat pumps around a building. It could be a number of heat pumps, maybe in a multi-residential development, or it could be multiple commercial buildings. So this is it could apply to all sorts of building types. Now, if we connect them all together like this, what we can do is we can assume that not all of these are going to be running at the same time. So we can take a diversity factor, as it's called. To give you an electrical analogy for diversity, if you're not familiar with the term, it's just like assuming that you're not going to plug a 3-bar electric fire into every socket in your house. You know, you'll be over designing the electrical infrastructure if that were the case. Now, the good thing about being able to take a diversity is we might be able to save a bit of borehole. So rather than having the 5 boreholes, we maybe need 4, as I've drawn it here. But the downside is that because the flow rate required by the heat pumps has to flow through a single header, then these pipes can get quite big. So the downside is you get larger header pipes the more you connect together. So an alternative approach would be to break the heat network up like this. So for example, I've drawn it here, 1 borehole between 2 buildings. Now, what we can't do there is take as much of a diversity factor in terms of the heat loads that we are looking to deliver, but what it does do is it keeps these header sizing down. So to give you an illustration of a real project, this is a project by Kenza Contracting that was done in Park Erin in Wales. And if I zoom in on this little crescent here, we've got 5 boreholes here, and they are serving 10 houses. So that's one array there on its own. Now, the interesting thing about, and that keeps pipe sizing down, as I say. The interesting thing about this, if I go up to the array 28 and 29 up here, is that whilst these boreholes here in array 28 are hydraulically not connected to the boreholes in array 29, they are actually close enough in proximity to each other to be in thermal contact with each other. So when we're designing a development like this, we can't just design each individual array and leave it at that. We actually have to design each individual array, but then look at the overall sustainability of that ground loop system that's being installed. So that's a flavour for the type of work that we get involved in. About 40% of what we do would be geology. About 20% would be how much collector do I need to put in the ground, how much borehole do I need, and about 40%, actually the majority of the technical work we do will be based around the hydraulics of the system. So that's by far the biggest bit of the work that we undertake. Anything on the chat, Duncan?
Yep, Simon's in with a question. Can thermal stores be used to meet peak demand and subsequently reduce heat pump capacity requirement?
Absolutely, yes. Yeah. So yeah, thermal store is a very good way of reducing that peak demand. The other way, of course, of reducing peak demand is looking at the control strategy as well. So quite often what we'll be doing is looking at maybe an hourly load profile. We'll see very high peaks on a Monday morning for a couple of hours as the building's taken up to temperature. What we could do is say, right, let's not warm that building up over a couple of hours. Let's use an overnight setback set point on it, or indeed having a longer warm-up period. So there are various different strategies for reducing heat pump size. And of course, the benefit of that is not just cost saving on the heat pump, but potentially you're going to be reducing your borehole requirement as well. So it is a win-win, and it's very important to look at those types of considerations when we are looking, particularly in commercial buildings, I would say. Great question, Simon. Thank you. Gonna move on, Duncan?
Yep.
Yeah, okay, cool. So just to say that, these types of heat networks are incredibly flexible. And the point of the drawing here is to say, let's say this is a supermarket here that could be putting heat into the ground loop. It could be taking heat out of the ground loop, but the heat that that supermarket's putting into the ground loop could be taken out by other homes and businesses on the same heat network. So they are a very natural way of recovering energy, even at incredibly low temperatures. And what we can do then is take that a little bit further, whereby we can actually connect these networks up together to take advantage of energy recovery even between them. So just with the application of a simple heat exchanger between two heat networks, then we can allow energy to naturally flow backwards and forwards between those two heat networks. And again, why stop there? What we could do is we could look at, say, some industrial waste heat that's going on that could be injected into a ground loop. And that heat can be at a very low temperature. So it can be a very flexible way of improving efficiency, reducing the costs associated with cooling that industrial process, and so on. So it's very much worth thinking out of the box. We're doing quite a lot of feasibility studies at the moment for the likes of universities, where they've got a big greenfield space in the middle of their campus, and they're looking at putting that ground loop infrastructure in, and then potentially exporting heat off their campus as well, not just serving their own buildings. So it can be a very, very flexible infrastructure. Another point to make is that we can actually connect these networks. They're sometimes called fifth generation heat networks, but we can connect those very low temperature networks to previous generation networks as well, which can give benefits to both the efficiency of the fifth generation network and the older heat network as well. So again, very, very flexible in terms of how they can be deployed. Anything coming in, Duncan?
No, you're clear.
Okay, look, I promised you then to talk about other sources. So far, I've been talking about vertical boreholes, closed loop boreholes. So that's simply a borehole drilled into the ground. To answer the question earlier, most commonly we're drilling between 100 and 300 meters deep for these boreholes. And most commonly inside each borehole, there's a single U-tube of polyethylene pipe installed. And then that borehole's filled with a cementitious grout again. So the water can then just flow up and down, forming that heat exchanger. The diameter of these boreholes is very narrow. It's only about 150 millimeters across. And there's very little construction to these boreholes. They're really just installed, the pipes put in, the grout is installed, and that's pretty well it as far as structure is concerned. So it's the most ubiquitous way of getting involved in the ground for certainly larger buildings. There are, however, other options. So for example, we could use trenches. So you'll see these mainly in houses being installed, but trench like so, and it might have some pipes installed in the bottom. You see a lot in the magazines, you'll see slinkies with coils of pipe in there. Not as keen on them. There's quite a lot of pipe in quite a small area, so they're a little bit more intolerant to changes in building loads, for example. And these pipes would be simply connected like so, up and down the trench. So very simple way of putting pipe in the ground inexpensively. They are less expensive than boreholes typically, but also they take a good deal more space than boreholes do. So again, closed loop vertical boreholes, closed loop horizontal. There is another option for closed loop, which is when we get into using water. So we can put a heat exchanger in any body of water, and we can take heat out or put heat back into that body of water just very, very simply by warming up that water or cooling it down. And as long as we make sure that there's a balance in these systems, so just like closed loop, we're looking for energy flowing in and out to balance what we are doing. In this instance, the main gain is actually solar radiation. So solar gain is the main gain in a lake. And actually, the main way of getting rid of heat is evaporation. So it evaporates the water to get rid of any excess heat that's put in. Now, these systems can be very, very cost effective. When you start talking about multi-megawatt projects, maybe a business park or a multi-residential project, then actually including the excavation of lakes, even new lakes, into the landscaping plan can be a very effective way of installing ground source at lower cost than boreholes, for example. So that's the final type of closed loop system. Could be canals, could be rivers, could be the ocean, and so on. Duncan,
it might be worth adding there, given the sort of the audience we've probably got with sort of projects looking at high-end individual dwellings, that properties with a decent sized pond can often be, the pond itself can often serve the building loads more than efficiently. And rather than a heat exchanger plate, it would be like the slinkies that you'd normally put into a horizontal trench, and they would be secured to the bottom of the pond and then headed back up to the house.
Yeah, absolutely. Yeah, so even small bodies of water are remarkably powerful in terms of the heat output that they can sustainably support. So just a quick word on permissions, because I'm coming on to permissions in a second. If you own the body of water, then there are no statutory requirements to get permission to get involved in this. Generally speaking, though, you'll be doing some planning applications, so the Environment Agency will be notified as part of that. But it's a tick box, really, that one. So that's all closed loop systems. Let's now talk about open loop systems. So this is where we're taking water from the environment, running it through a heat exchanger and putting it back down. So what I've drawn here is an aquifer system. So we've got a borehole here that's drilled into the aquifer. Much bigger piece of construction this than the closed loop alternative. These could be up to 2 meters across. They could be lined in steel or stainless steel down into the aquifer. They might have filtration and so on built into them. So a much bigger proposition in terms of construction. But they can support, even a single pair of boreholes that I've drawn here, can support much bigger loads than the individual closed loop variety. So as I say, all we're doing is taking heat from the ground through a heat exchanger and then back into the ground again. So it is a loop because this water will gradually migrate over because of the hydraulic gradient that we're putting into it, but it's got an open portion. Now, because we are dealing with untreated water now, the fluid we put into a closed loop, we know exactly what it is. It's clean water. It's got antifreeze and inhibitors in it. But in this instance, because we are open to the environment, we don't have the opportunity to treat that water. So that has implications in terms of maintenance of these pumps and these heat exchangers, for example. Now, depending on the aquifer, the maintenance of pumps and heat exchangers could be a matter of months. It needs between maintenance visits, but more commonly, particularly like in the southeast of England with a chalk aquifer that's under London, then it might be 10 to 12 years between maintenance visits required for these systems. So that's something that's got to be considered anytime you're looking at open loop, is the maintenance. Now, we can do open loop from surface water as well. Canals, rivers, even the sea can be used for open loop as well. Again, you've got those maintenance requirements to consider. And the final point to make on open loop systems is that above 20 meters cubed a day of water going through the system, there is a statutory requirement for licensing from an Environment Agency in England and from SEPA up in Scotland. So that licensing process can take well over a year, and it can be quite cumbersome to do so. So just bear in mind, whilst open loop can be very good from an install cost point of view and from a space point of view, because you only need these small boreholes, the only, a manhole really is all you have after the event of the installation. They can be disadvantageous in terms of the licensing requirements for it.
Yeah. To give you an idea, 20 meters cubed per day will allow for probably a 20 kilowatt system.
At the most. Yeah. So if there's no more questions in the chat, then I'll just
there is one question on heat networks, Chris, before we go on to one new change. Regarding the ownership of heat networks and who is responsible for the management of the networks once they're installed. Are there management charges? Who is driving the uptake for the networks? What are the current blockers for more universities or landowners, developers for considering these networks?
That's an excellent question. Okay, so it varies in terms of ownership. So, for example, the universities we've been talking to, they would like to own that heat network and operate it and then charge either access charge, an annual access charge, or a per kilowatt utilisation. We're working with a number of housing developers at the moment as well, who are looking to build out these heat networks and then own and operate them in the long term. There are other customers of ours, such as Metropolitan, for example, who own and operate large-scale heat networks. They are looking at heat pump networks now, which will be owned and operated. And as I say, it'll either be an access charge on an annual basis. So, you've got a 1-bedroom apartment, you're going to have a smaller access charge than a 5-bed house, for example, or it could be pay per kilowatt hour of heat, just like any other heat network. There are other ownership models as well coming into it. So pension funds, for example, really like to look at longer term assets, maybe 40, 50, 60-year assets that they can own and operate in the long term. So yeah, excellent question. It does depend on the architecture. What was the second bit of the question, Duncan? Remind me. I think you're on mute, Duncan.
Thank you. What are the blockers for universities or landowners, developers for considering these networks?
Well, I think, investment cost is a key blocker. Obviously there's a cost associated with installing the infrastructure. It is a long-term asset, as I'll come back to in a few moments, but cost would be the blocker. In terms of geological blockers, very, very unusual that we would go back to a client and say that, you can't do ground source. There are some circumstances under which it could be dangerous to drill, for example, if there's high pressure water in the ground, but in most cases that's not a consideration for us. And then risk, people do tend to see it as a new technology, even though it's very old technology. People do tend to see it as a new technology, and so there's risk associated with it as well. And then finally, there's getting the commercials sorted out is not straightforward. So for example, what we're doing at the moment is a number of retrofit towns. So an infrastructure is being put in around the streets, underneath the streets of towns, and then that access to that ground loop is then being offered to the customer. Now, obviously, what you're doing there is you're dealing on a house by house and a customer by customer basis to try and get that heat network deployed. So it can be a little bit more challenging commercially to get that to happen. And there is a thing under consultation at the moment that you may have heard of by government, which is heat network zoning. And what that looks like it will be is it will give local authorities the opportunity to declare a heat network zone, and these types of networks will be applicable there, and there'll be some degree of compulsion to connect to that network. We don't know the details of that yet, but it will come out during the course of this year. For example, if you go to the average supermarket and say, would you like to reduce your cooling costs by accessing this heat network, they'll probably say no, because they just see it as something that they've not done before. Whereas if they've got some degree of compulsion to do it, then it's a different story. So moving landscape at the moment on that one. Great question, so thank you.
Lovely. Pete's in with a question which we'll answer on a later slide.
Excellent. Okay, cool. So I'm just going to talk about the system. This is in London. It's one new change. It's been up and running for about 15 years now. It's owned by Land Securities. If you imagine looking east from the dome of St Paul's Cathedral, it's just at your feet there. It's a lovely building. Mixed use building. It's got offices on the top. It's got some floor of restaurants and so on, and then it's got shops down at ground level. The brief on this project was do the maximum we can do with the ground available to us. So what we did in this project was we put loops in the piles of the building. Now those loops in the piles are in the London clay, and the London clay is quite a low conductivity ground condition, but it's got a very high specific heat capacity, so it can store energy extremely effectively. So that's our interseasonal energy store that we can store heat between winter and summer in. We've also got, it's a bivalent system, so we can actually schedule loads on and off to suit, so we can take cooling energy from the building and put energy back in as well. And by doing that, I'm running the open loop wells, which are connected via a heat exchanger to the closed loop. We can manage that ground loop temperature. And so what we're doing is effectively managing that temperature around 20 degrees C all year round. And what that does is it puts us in a really nice sweet spot of efficiency between heating and cooling, i.e. it's the point at which the cooling efficiency and the heating efficiency are maximized around that 20 degrees C. So what we're seeing on the system, the last time I saw some numbers on it, we were getting a COP in cooling of 6.8 and a COP in heating of 4.8. So huge efficiencies on the system. Sorry?
Worth mentioning they're seasonal.
Yeah, that's a seasonal COP. I'm going to come back to talking about the difference between a coefficient of performance and a seasonal coefficient of performance and the relevance to heat pumps in just a second.
Why wouldn't we have wanted the closed loop ground loops to go beyond the London clay?
Well, we could have done, but what is going on in the Chalk Aquifer here, the water actually is in the cracks and fissures in the top 20 metres of the chalk, and there is movement in that groundwater. So if we had gone into the chalk with deeper boreholes, for example, then we would have been washing that heat away, so it wouldn't have been as an effective energy store. as it is inside the London clay? It's a great question. Thank you very much indeed.
It was mine.
That was yours. Well done, Duncan. You are learning. Right. Okay. So I'll drop back into the presentation now, and I'll start away with, I think it's myth busting. So we've talked about ground freezing before. You know, if you're freezing the ground, if you're seeing any adverse conditions as a result of ground loops, for example, you know, grass not growing on top of them, that's just a poorly designed and installed ground source system. There are so many reasons why people give, and spurious reasons why people give why you can't do ground source. So for example, we've got hard rock, we've got coal mines, we've got archaeology, we don't have enough space, all these reasons why ground source can't happen. And you do tend to see it in reports from mainstream consultants who don't have the specialist knowledge in this sphere. And the truth is, what they should be saying, I'm being a bit flippant here, but what they should be saying is, we can't do ground source because we don't understand it, not because you don't have space. I see so many spurious reasons why it's been rolled out, which is a shame, really. A colleague of mine in Canada actually did an piece of analysis with a university over there for the North American markets, so Canada and the US, and he reckoned that about 80% of viable ground source systems were ruled out at early stages because of either poor application of rules of thumb or poor knowledge on behalf of who was assessing the system. I've seen, for example, multi-megawatt systems ruled out on the basis that you can't get enough horizontal trenches in there. You know, multi-megawatt systems with horizontal trenches are never going to work. It's just too much space. There's a really interesting debate around reliability and complexity of systems. So balancing reliability and complexity. It is natural, I think, for people to over complicate ground source because it's seen again as new technology, but that can affect your reliability. So it's very important to make rational decisions about reliability. And we can really build resilience into a ground source system that goes well beyond what you can achieve with any other heating and cooling technology. And we do a lot of prisons, for example, which have got some of the highest requirements in terms of reliability of any projects we do, even more than hospitals, for example. And the way it was put to me by the folk in the Scottish Prison Service, we're just working on HMP Highland at the moment up in Inverness. The way it was put to us there is, yeah, if you've got a hospital, the patients don't tend to riot if the heating goes off. So, you know, it is a very serious consideration when we're looking at reliability in the systems. Talked about archaeology, absolutely can't be dealt with, no problem at all. It may require an archaeologist to be on site when the top few meters of the boreholes are being installed, but that's the worst of it, really. One thing we get quite a lot of is people coming to us with what we call miracle loops, or I call miracle loops at least. And somebody comes along and says, I've got this new ground loop technology, new installation of ground loop that's going to give you 6 times the energy of anything else. What I can absolutely categorically tell you is that if the ground won't give you that heat, you cannot take it out of the ground. You will create an unsustainable system. So I'm always very skeptical of people who claim that their ground loops can give you a lot more than anything else in the marketplace. Yes, if the ground conditions are right, that may be the case, but you know, let's be straightforward about that. Talking now about the difference between coefficient of performance and seasonal coefficient of performance. Coefficient of performance is a spot of performance at a given set of temperatures. So for air source, the standard rating point is 7 degrees on the air temperature and 35 degrees in the water temperature going into the building. For water source, it's 0 degrees on the source side and 35 degrees on the load side. But that's just at one point of temperature. The difference between that and seasonal COP is that to get your seasonal COP, you need to divide the annual heat put into the building by the annual electrical consumption. So it gives you a much more precise assessment of the relative performance of systems. And again, we regularly see ground source being written off because people are considering COP and not seasonal COP. In order to model seasonal COP, you've got to be doing ground loop modeling, and the design software does spit that out. Life cycle costs are what it's all about. And what we're seeing now with the fuel prices we are now seeing is that ground source compared to air source, for example, within a 8 to 10 year period is about half the overall life cycle cost of air source. So a significantly lower cost of ownership, but obviously you've got the installation of the ground loop to consider, so it is a higher install cost. Space required, again, is often overstated for ground loops. And then just finally, talk about house by house. I do a lot of lobbying work on behalf of the Ground Source Heat Pump Association, and it does frustrate me that civil servants and politicians do tend to think of it's zero carbon on a house by house basis, so individual owner occupier houses. If you try and do ground source on a house by house basis and roll it out to the masses, then it's a hugely expensive proposition. If you start now to look at street by street and town by town, then the economics change completely. So it's really important those economies of scale coming into the installation of ground source, particularly when we look at now what we're getting into with mass rollouts. Couple of final points to make. Solar and ground source heat pumps is a natural combination. So what we could do is a fairly trivial one. We could put solar PV, photovoltaic on the roof, and that electrical energy would then contribute to running the heat pump. So fairly trivial interface of the two technologies. Bit more subtle and very interesting is if we've got a ground source heat pump with a borehole on it like that, for example, we could pop a heat exchanger in there and put a solar thermal connection into that. So what we're now doing is we are increasing the temperature of the ground. So we're improving the efficiency of the heat pump system for very little extra installation costs, given the cost of solar now. Really fascinating. Takes the average seasonal COP from around 4-ish for a non-solar assist to over 5. And we are seeing some really good results from monitored installations that we've had in for a few years on that. So always worth thinking about, be it on a domestic scale or on a commercial scale, that one. Going deeper, so what I've been talking about so far is that this 100 to 300 meters deep, and down really deep when you're into this 3 to 5 kilometers, you can start generating electricity. But there is a middle ground of depths, somewhere around 800 to 1500 meters, where we are getting some elevated temperature as a result of the geothermal gradient coming from beneath, but we're not at the temperatures we're able to start generating electricity at. And that's the area that we're pushing into at the minute. So what we're doing there is we're borrowing technology from installation in the oil and gas industry, but also we're actually looking at repurposing onshore oil and gas wells. There's over 300 onshore oil and gas wells in the UK alone, and they are tended to be coming up to end of life. And so rather than decommissioning that at quite large cost, between £1 and £2 million to decommission an oil and gas well, we can actually recommission it to become a heat generation asset. So a very interesting kind of connection between the oil and gas industry and what we're doing in ground source. And then finally, ground loops as an asset. Ground loops, if you start looking at them as if it's like the broadband networks, the water networks, the gas networks of old, and the electricity networks, you start to install them and operate them over a long period of time, then the economics of ground source completely changes and becomes far more like the types of investment that the gas, water and so on companies have been making over the last few years. And that allows, for example, us to go along to a developer. You're building 1,000 houses, you're considering air source or ground source. That's really your only, well, direct electric if you can get away with it, but you're not going to be able to put gas connections in. So it's air source or ground source. If you third party own and operate that ground loop, then ground source becomes a less expensive installation than air source. So it's a very different way of looking at it, and actual projects are now going in with just that business model standing behind it.
So to answer Peter's question, what is the typical lifespan of a heat pump system?
Yeah, absolutely. So the ground loop itself, over 100 years is the quote on it. The half-life of polyethylene is something like 10,000 years. It's going to be there for an awful long time. So it's the long-term asset. The heat pumps themselves, air source in the UK climate, because we've got a maritime climate, will be somewhere around 10 to 15 years, something like that. The ground source heat pumps, because they're in a plant room, they're not exposed to the elements, will be 20 to 25 years for the box itself, for the appliance itself. So, yeah, great question.
Lovely. Open forum for more questions.
Yeah.
Feel free to use the raise hand function on Teams if you've got a question, and you can ask away.
Yeah, absolutely.
Or just unmute yourself.
No, thanks, guys. Just wait whilst we wait for a couple more questions.
Yeah, sure.
2 or 3 minutes. That really interesting. Thank you, Chris. I mean,
pleasure, Simon.
actually what the link that Duncan uploaded from Kenza was interesting because, and then your point, because I was going to ask about, who's driving, well, I already did, but who's driving this change? How can it become more prevalent? When it comes, from a street by street perspective, I presume it's the equivalent of the gas board going in and just closing down the streets and just doing a shed load of work. So it's not going to come without any inconvenience, but presumably it's the future. It's going to happen and it needs to be done. And I was just blown away by the ability to use these small bodies of water as well. Yeah. And if developers can start planning to put in ponds, lakes, etc. Yeah. So again, one of the blockers is how is there a knowledge gap? Are people aware of this? When the big developers, presumably they are, but the big developers, they're slow on the uptake. It's more the SME developers that ones are thinking about sustainability, but it's the big developers who can do it, but they're not. So
it's very interesting. There is a huge knowledge gap, Simon. So that's very true. So we've just last year finished a series of 17 digestibles at 10 to 25 minute videos, which are being hosted by the Ground Source Heat Pump Association, and that's aimed at consulting engineers who maybe know a bit about the technology but don't have the knowledge. And that's all about how do you as a consulting engineer get enough knowledge to do a first tier assessment of property of the systems, but also then look at how do you engage with the supply chain to get more knowledge and those kind of things. So that's launched now at £1,600 to attend that session. We've got over 100 people signed up already. So there is a thirst for the knowledge in the consulting engineering community, but the knowledge gaps don't stop there. Policy makers have got a knowledge problem. Installers, the average plumber, most boilers are installed by plumbers to repurpose the heat pumps. They're behind the curve on that. Then you talk about the end user, the customers, like the developers. There's a mix there. So many of the bigger developers are getting involved with the likes of Kenza. I was at a reception at the House of Lords late last year, and I was started talking to two developers who are there specifically because they have a relationship with Kenza. So a lot of them are establishing those links as well. I'll mention Telford Homes, for example. I went to their board meeting just before lockdown, did a presentation to them. Their sustainability director stood up to do the introduction and said, Ground Source is what we're doing now. These are the team to deliver it for us. So there's a range of different attitudes towards it. Let's face it, some of them are just going to do gas boilers as long as they possibly can.
Sure. Yeah.
Like double glazing. It became a legal requirement before many of the developers considered it. So that's where we are. But what I would say is, we've gone from 4 people to 10 people within the course of last year. So we're growing significantly. And because of the type of work we do when we're getting involved in feasibility early doors, if we're busy, it means the market's on that growth trajectory. So it's an education process every day, of course, to overcome that. But
no, it was I thought it was fascinating. Thank you very much. A lot of content there. It's really appreciated. And we focused a lot on air source heat pumps in the last quarter and less on ground source. So it was good. It was good to have this chat, and hopefully we can have a follow-up session as well. I don't know if there are any more questions, but we are hitting 1 o'clock, so I know people like to keep their webinars within the timeline, within the set time frame. So no, thank you very much all for attending. Sorry for the technical problems at the start, but it was very appreciative of for you guys to join. Thank you very much.
Absolute pleasure, and thank you so much for all the excellent questions and your attendance today. So thank you very much indeed.
Cheers, guys.
See you soon. Bye bye.